Hello, my name is Sam. I am an online maths tutor, and this is a video about volumes of revolutions in further maths. So this is an A-level video, which will employ the Year 12 integration techniques for volumes of revolutions. So let's get started. So I have some function here which I have plotted on a graph, and what our question is going to ask us is to work out the volume of the ultimate solid created when this curve is rotated around the x-axis. Indeed, in a question, the curve can be rotated around the y-axis, but for the sake of this video, just for now, I'm going to talk about the x-axis. So how do we do this? Well, we're rotating a curve around about the x-axis, and we're finding out a volume. So first, it's useful to find out some sort of area, and then figure out a volume. So our volume calculation is only going to be between two limits. It's not going to be for the whole curve, because that would be infinite if it was rotated all the way around the x-axis. So what I'm going to do is just draw on some lines here at some x coordinates. And this distance here is our change in x. So this is our delta x. So this is x and this is x plus some value a. And the inside area here is delta x. So this is the change in x from x to x plus a. Now this is a small strip of volume of our curve. And what we want to do is we want to calculate the volume, but let's start with the area. So the area of this is going to be our delta x times by the height, so times by y. So delta x y. And that's for the size of this strip. Of course, this is going to be a trapezium, which can link back to the trapezium rule. However, we don't want to have to deal with trapeziums because that means we're going to get an approximate result. We want to calculate the exact area that is going to be generated when this is rotated a certain amount around an axis. And to do that, we're going to try and make delta x as small as possible, such that delta x is just a line. So where delta x becomes 0, it approaches 0. Therefore, that is a limit. So the area of this little bit here is a limit. But that is the same as an integral. So that's the same as just calculating an integral at one point on a graph. We want to start by looking at volume. So the volume of this segment, when it's rotated around the x-axis, is going to be pi times by its radius squared. The radius here is y. So pi times by the radius squared times by the height, which is going to be our delta x value. So we have pi y squared times by delta x. Now, like I said, we want delta x to be small. We want delta x to be as small as possible. And then to calculate the total volume, you're going to add up the strips within a certain limit. Sound familiar? From A to B are two limits. We're going to add up all of the sums of these individual little strips of volume which we have calculated. That sounds like a limit of a sum, and a limit of a sum is the same as an integral. Therefore, the volume between two limits a and b is equal to the integral from b to a of pi times by y squared dx, since we are integrating with respect to x. We can pull pi out of this equation, therefore this is equal to pi times by the integral from b to a of y squared dx. And so we can pull the pi out of this integral and say that it is equal to pi times by the integral from b to a of y squared dx. And this is going to be our calculation for a volume of revolution. So given any curve where y is equal to fx, the volume of revolution, so the volume of the curve between two limits when rotated 360 degrees around an axis, is going to be pi times by the integral of y squared dx. This does also work with the x-axis. So if you are rotating 360 degrees, it also works with the y-axis. If you are rotating 360 degrees around the y-axis, then the volume is going to be equal to pi times by the integral from b to a of x squared dy. This does also work for parametric integration, so you may not see parametric integration, at least not with volumes, until year 13 if you are a year 12 student watching this. But it's going to be equal to pi times by b to a. I'll just do it for y squared here. It will be y squared, and instead of being dx, it will be dx dt, just saying that dt is your third variable. This could be c, it could be a, b, whatever. And then dt, where you change your limits here. So the t needs to change these b and a limits so that they are in terms of t and not in terms of x. But this will still work with parametric integration, and you will have to do that in year 13. Okay, so let's move on and look at some examples. So calculate the volume of the solid generated when the following curves are rotated 360 degrees around the x-axis. So that's what we've just looked at, and that's going to use the equation which we've just derived, where v is equal to pi times by the integral from b to a of y squared dx. These questions can be quite simple. The calculation, or at least the formula, is not the hardest thing to memorize in the world, but sometimes the integration used, especially when you get into year 13, can be quite complicated. But for this example, it shouldn't be too bad. We're just going to test the waters here. So the volume of our revolution is going to be pi times by the integral from b, which was the larger number here, 2, to a, which is 0, of y squared, so I'm going to put in 10x squared, and I'm going to square it, dx. So this is equal to pi times by the integral from 2 to 0 of 100x to the power of 4 dx, which is equal to pi, and then we're going to compute our integral, so 100x to the power of 4 integrated, we add 1 to the power and divide by the power, so 100 divided by 5 is 20, so 20x to the 5 between 2 and 0, and that is going to be the calculation we need to do. So pi times by, this is going to be 20, 2 to the power of 5 minus 20 times by 0 to the power of 5. Now the 0 is going to cancel, so this is going to be pi times by 20 times by 2 to the power of 5, which you can calculate on your calculator. And our answer is 640 pi. So not too complicated. The integration is the hardest step here. But yes, this can be taken much further in future topics with parametric integration and with other bits of trig integration and all sorts. So let's try another example. So we've got y equals 1 plus 1 over x squared, and we want to calculate the volume of revolution between x is 1 and x is 2. If you want to try this yourself, then pause the video and just give it a go now. Otherwise, I will start calculating it. So our equation is y equals 1 plus 1 over x squared. Our integral is going to be pi times by the integral from 2 to 1 of 1 plus 1 over x squared dx. Now let's calculate y squared. So y squared is this part here in the equation. So this is going to be 1 times 1 is 1, then 1 over x squared times by 1 plus 1 over x squared times by 1 is going to be 2 over x squared plus 1 over x to the power of 4. Now this is equal to 1 plus 2x to the minus 2 plus x to the minus 4. I like to put it in this format just because it makes it easier to see what you're doing with the integral when you're adding 1 to the power and you're dividing by the power and all sorts. You can also do this in the step here, so you can make this x to the minus 2, which can make it a little bit easier to deal with. So let's sub that into our equation. So we've got pi times by the integral from 2 to 1 of 1 plus 2x to the minus 2 plus x to the minus 4 dx, which is equal to pi times by, now the 1 integrates to an x, the 2x to the minus 2 becomes 2x to the minus 1 divided by minus 1. This is minus 2x to the minus 1. This becomes a minus 3. So minus 1 over 3x to the minus 3. And that is between 2 and 1. And you can put this into your calculator, but it's important to write out the whole thing first. You may lose marks if you don't write out the full substitution. I have lost marks because I haven't written the full substitution before, so I'd recommend doing so. You can then calculate your answer using this calculation. I'm going to do this on my calculator. So we have pi times by 23 over 4 minus 4/3, so plus 4/3. So pi times by 23 over 24 plus 4/3 is equal to 55 over 24 pi. And that will be your answer. That is the exact answer. Always leave your answer as an exact form, unless it asks you explicitly to put it in significant figures or decimal places. It is always customary, and is generally the thing to do to leave it as an exact answer. So let's move on to our last example. This one is slightly harder, but mainly just in the way that it's written. Again, the integration shouldn't be the problem here. So we are calculating the volume of revolution of y equals 3 minus the cube root of x between x is 1 and x is 8. And this is when it's rotated 360 degrees around the x-axis, because that's what the question originally asked. And I'm going to calculate y squared here before I write out the integral, just to make things easier for me. So this is 9 minus 6x to the third plus x to the 2/3. And then our volume calculation is going to be pi times by the integral from 8 to 1 of this horrible polynomial, although you will come across much worse. And this is equal to pi times, and then we've got to integrate this, so we're going to add an x onto the 9x. We're going to increase the power by 1 to make this 4/3. Dividing by 4/3 is timesing by 3 over 4. 6 times 3 is 18, over 4 is 9 over 2, x to the 4/3. Plus, add 1 to the power here, this becomes 5 over 3. So this is 3/5 x to the 5 over 3. And this is between 8 and 1. I'm going to write out our full calculation here. So this is our full calculation, and then we are going to want to simplify these individual terms. Notice here that when you are subtracting the 1, or if you're starting with 1, then usually you can just write the coefficients of your x terms, as the x term is just going to become 1 no matter what the power is. And so this is the simplification of our integral with the substitution completed. All you need to do is do the subtraction. Okay, and that is going to be our final answer. So all three of these are left in their exact answers. And as you've probably seen, the integration here is not necessarily the hardest part of the question, but that will quickly become the case when you do harder examples that use more complicated curves, and the limits as well can become more complicated too. And just remember that if you are dealing with parametric equations, to do the correct conversion of your integral, and also be cautious for any improper integrals, as you cannot calculate a volume of a revolution for an integral which is improper. Thank you for watching. If you liked the video, please do subscribe. Let me know in the comments if there's anything you would like me to cover, and also do tell me if I get something wrong. I will make mistakes. I'm not perfect. Thank you for watching.